So are you able to see the screen, guys? Hello, good afternoon.
Yes, sir. Good afternoon, sir.
Okay, मैंने कहा जब तक बाकी लोग connect होते हैं, if you have questions uh, related what we are doing, so you can ask it. Did somebody try to look into that question 17.2.2?
Yes, sir.
That actually it's not a question, sorry, it's an example 17.2.2, right? So you'll see six matrices are given 3 by 3, all of which are nothing but the representation of your dihedral group D3. And once you get the representation, you see that these were not the diagonal matrices. So what is given in that question, that there exists generally a unitary matrix, since all the matrices before that were also unitary. So I mean those six matrices. So there exists a unitary matrix which can simultaneously diagonalize. We do not care if one of the matrix gets diagonalized or two. It should be all six matrices should be diagonalized together with a single matrix. If so, then all six of them will be reduced to diagonal. If they are already diagonal, then of course it will be, let's say, left unchanged. If it is not already diagonal, then it will be diagonalized. But the interesting thing for that non-abelian group is that you get a form which is not exactly diagonal matrices, but it is what we call as the block diagonal matrices. That is, if you choose any block of matrices, those block of matrices are diagonal with the zero components coming up between those. Now, why I said that in quantum mechanics it was important? Because in quantum mechanics, whenever you look for these kind of matrices which are block diagonal, basically somehow gives you an idea that the wave functions, I mean, again, this portion is not exactly related with your examination, but the physics wise, that whenever the diagonal things come, it tells you that the interference between the terms, between the diagonal and the other diagonal is zero, because there are the cross terms which are basically zeros. It's only the diagonal term which is there. So diagonal terms correspond to something that without interference there exists certain wave functions, which in other sense it means that a particular wave function gets invariant by that particular transformation. So I mean, it's a very interesting way of thinking about a linear vector spaces which are basically orthogonal, and you are thinking now in terms of the diagonal matrices only. That is, that if an operator is represented by block diagonal matrices, that means that the wave functions or the function eigenfunctions are such that there is no interference between that. That means we are talking about something like orthogonal wave functions. So it's very interesting concept in terms of building basis set. But for us in group theory, the block diagonal form tells us that it is the now that we have got the representation, I can write down my original matrices in terms of the direct sum of irreps. In fact, it writes further that there is no further reduction possible for those matrices, which means that the direct sum will compose of one 1 cross 1 representation and another 2 cross 2 representation. And the reason being that it's a non-abelian group which is represented by these unitary matrices. So we are not going to get this 1 cross 1 representation, irreducible representation for all of it. We will get part of it 1 cross 1 and part of it 2 cross 2. So that's what it is trying to show you. In fact, the example immediate after that, 17.2.3, is what I am going to do here in the class. Anyway, so let me just summarize by this time what we were doing in terms of the continuous groups. I came up with this continuous group in terms of this O2. O2 is a group which is a continuous group now. Remember the R theta and the J theta. And what is the kind of continuous point we are talking about? Any any set of matrices which are leaving our length squared invariant is what constitutes the, let's say, elements of these guys. So it's the set of rotations, set of reflections, surely falls under this category. And then I say, okay, I mean, even though rotations and reflections are a good way to think about the physics, but if you look at the mathematical structure should be cleared by looking at these components 1, 2, 3, and 4, A, B, C, and D, all are real numbers. So in general, O2 group will have 4 elements. If there exist certain constraints in this system, then corresponding constraints will reduce the choices, the independent choices for these A, B, C, and D. And that can be understood just by looking at this OTO or OOT is equal to identity. You get this A square plus C square equal to 1, AB plus CD equal to 0. What kind of thing you can think about? You can always think about something like this, that A and C, if you think about a unit vector like this, which is of course I am taking the first column, then what kind of structure it has, A and C, that this A and C is going to form the normalized vector AC. This see, A square plus C square is equal to 1. What kind of a structure I have for B and D? That is also, see, B square plus D square equal to 1. So if I think about two vectors phi 1, phi 2, now what will be the product phi 1 comma phi 2 for this guy? So AC and BD, AB plus CD, what will it result?
Should be 0.
Should be 0, which is coming from this constraint. So what I have requested you to figure out, that if these guys A and C and B and D are forming some sort of orthogonal vectors, which of course orthogonal matrices do, then what will be the further relationship which will be there? So you will somehow find that the relation will come. So this B and D can be expressed in terms of A and C. So what will this reduce to? This will reduce to only 2 independent elements. And then further you will find out, oh, one of this constraint, which is the determinant of O equal to plus minus 1, will reduce the further choices. And hence this 2 with one additional constraint will be basically reduced to only one independent parameter in the case of orthogonal matrices. And that is where this term which I wrote here, n square, which for this case for 2 into 2 matrices turns out to be 4, minus n into n plus 1 over 2, which for this case will turn out to be 3. So with 3 constraints, 4 parameters, you will get only one independent parameter, and that is what we call as the order of this O2 group. And then I told you that of course that there exists a subgroup of O2, which we call as the special orthogonal 2 cross 2 matrices. And the word special corresponds to what we call as the rotation only effects. So the rotation only effects are the ones where the determinant of these 2 by 2 matrices is restricted to plus 1, and that is the special feature. That is why we call it SO2. So O2 and SO2 are continuous groups, both of order 1, where SO2 is a subgroup of O2. And each of this word stands for something. So O stands for orthogonal, 2 stands for 2 cross 2. Questions here? Okay, so you are going to read it further and then we will continue to make. Yes. So now I can extend it to O3. So we were talking about, for example, plane. Now you can talk about the three-dimensional space, let's say R space. So where R will be given by X, Y, and Z. And then of course you can do exactly what we did earlier. So that there exists a transformation. Now think about R prime is equal to OR. What kind of this O will be in this space? What kind of matrix it will be? But the dimension will be
3 cross 3.
Yeah, dimension will be 3 cross 3. So in the 3-dimensional real space, you can talk about these O matrices, which when you are going to impose this length invariant condition, you will get this OTO is equal to identity is equal to OOT. So we can basically do the same things what we have done earlier for 2 cross 2 matrices, and now we can again think about what kind of things can come. Physical transformation, it's a 3-dimensional rotation now. So how many independent rotations you can think about in O3 group? In O2 group, there was only one rotation. What we did, origin remained intact, and we just remember that it is something like a plane going there. Now in O3, what are the possibilities? Independent rotations.
Three.
Exactly. So what will be those independent rotations if one can think about? Those independent rotation can be, one is around the z axis. So if I take this as the z, this as x, and this is y. Another rotation which is possible along x axis, you rotate y and z. Another rotation which is possible is around y axis, which means which we are rotating in x and z. So we will have three independent rotations, and that will define the order of this group. Otherwise also you can think about it in terms of this n square minus n plus 1 over 2, where n square will be the number of components in the matrix. So 3 cross 3 matrices, how many real components will be there?
9.
9. And now
9.
impose this constraint n plus 1 over 2. So how many constraints you will be?
6.
So it will become
6.
9 minus 6, which will be equal to 3. So one can think about it from the rotation side, which is the physical one. Another one you can think about it just from the idea of the way you can find out the number of independent terms in orthogonal matrices, which will turn out to be 3. So orthogonal group O3 is nothing but what? Let me just write it down few things and then you can basically ask. So O3 will be orthogonal 3 cross 3 matrices, continuous group requiring 3 independent parameters, and hence we define the order of this group to be 3. What will be the determinant of this guy?
Plus minus 1.
Right? I
Plus
mean, these are the
minus.
orthogonal matrices, so this will still give you same. So under matrix multiplication. So then you can do something. Okay, let's just found a subgroup of this, and that will be something like SO3. Remember last time R theta, we already showed that R theta forms a group. Yeah, here I can again go something just like we did for O2, giving SO2. So S will be standing for special orthogonal. So what is this special thing?
So determinant 1.
Determinant equal
Determinant
to
to be
plus
plus
1. We will just retain that, and this will be orthogonal, which means OT is 1, sorry, OT, and 3 is the dimension. 3 cross 3 matrices now. And this way, in fact, now one can even think about what will be the order of this. And interestingly, this guy will have the order what? SO3 group will have the order same as the order of the original group or one less of the order. This is something which I would like you to work on before I commence on that. So please do it as a homework. Think about how many independent parameters do we require. O3 we already discussed 3, right? So what about SO3? Is it 3? Is it less than 3, 2, 1, whatever? So these are nothing but the additional constraint here is determinant plus 1. But remember that there is a constraint already which was imposed on O3, which was determinant O is equal to plus or minus 1. And this way one extends it to the group of matrices ON and SON. So can somebody quickly tell me what is ON and what is SON? ON.
Orthogonal dimension n
Orthogonal
cross n.
N cross N matrices. And under what group composition क्या है?
Matrix multiplication.
Exactly,
Matrix.
under matrix multiplication. Excellent. Matrix multiplication. Okay, and this will be a continuous group. And what will be the order?
N.
N square
N.
minus n into n plus 1 by 2.
This I have already given to you because I was doing only the examples of that. And what will be this guy? SON then?
Orthogonal n cross n matrix with determinant 1.
So this is a subgroup. Let me just write group. So subgroup SON, S is just the additional thing which is determinant of these matrices will be restricted to 1. And they are again, I mean, this is called the proper rotation group in some books, but the reason is clear. So there exists a generalized groups ON and SON forming what we call as the continuous groups. Now, I hope, I guess you are doing angular momentum in your quantum mechanics. Yeah.
Yes, sir.
Yes, sir.
So at this point, I can just invoke a sentence, and that sentence itself is kind of, I would say, a topic in itself. That SO3, which is what the rotation, remember this rotation in three-dimensional space. This SO3 or O3 is a group representing angular momentum operator in physics. Remember, you need Lx, Ly, Lz, three angular operators. And these three operators basically constitute the whole angular momentum algebra. Now, people who do group theory, they understand that it is nothing but since it's a three-dimensional rotation and we know that the rotation about the origin leaves the length invariant, that there is a natural consequence of the invariance of the square vector or vector squared or the length squared due to rotation, and that is what we call as the SO3 group or O3 group. And then for O3, in fact, you will find out for SO3 group, you will require three independent elements, and those three independent elements will be defining the order of the group. And the Lx, Ly, Lz or Lr, L theta, L phi, what we write it is nothing but the representation of these three elements in this. So how to even think about now angular momentum? Angular momentum can be easily thought of the invariance of a square vector or length squared under rotation in three-dimensional space. That's, I mean, equating things, but okay, I mean, at this time it is just a statement. I'm not doing anything here. I am just telling you. Okay. So questions here so that I can actually move to complex spaces.
So can you just once repeat the invariance wala line?
अच्छा हाँ बिल्कुल बिल्कुल बिल्कुल. See, when you are doing this linear transformation O, at this point there is no invariance, right? R prime is equal to OR. Any linear transformation is happening. When you are invoking this R dash square is equal to R square, what are you saying actually? That this operation O or the operator O leaves the, oh sorry, length squared invariant, right? That
Yes, sir.
whatever be O be doing, it is not affecting the length. And the consequence of this is this orthogonal OT O is equal to I. Originally, could have been anything, any 3 by 3 matrix. But now the imposition because of this R prime square is equal to R square. Remember what we did earlier, R prime T times R prime is equal to RT is R. So this is what the imposition is coming from, orthogonal portion. So whenever there is this invariant of distance squared, there results in an orthogonal set of matrices, right? So angular momentum, when you are saying that it's a conserved quantity under the point that your object is or the physical laws are invariant under rotation, what do you mean to say when you are saying that invariance under rotation? This is what you are saying actually. Fine for angular momentum.
that the length of the angular momentum vector is conserved.
No, length of
If we
any
rotate.
vector which you take in three-dimensional space, if you rotate it by any angle, this remains conserved. Not angular momentum
Okay.
vector. Angular momentum is coming as a consequence. Remember, you need three independent parameters to apply, do that. And I will actually relate it. I mean, even though I am left with only two classes, but I think I will be able to do something on that as well. But you understand, it is the length squared which is invariant. You can make any rotation, and length will not change as long as I mean your rotation is about the origin. Correct?
Yes, sir.
So this is a symmetry, right? I mean, there is a symmetry which is existing, and hence there has to be a group. So this is how people start thinking about the groups. So now, I mean, intuitively, if you can think of, then what could be the way? I can think about just the sort of invariant transformation, and then correspondingly there exists a group, or otherwise, I can think about a group of operations which leave something invariant, and correspondingly this will result in something interesting. Yeah, in physics, group theory is related with symmetry. This is what the first thing which I wrote, group theory and symmetry. That symmetries and group theory are going hand in hand now. Parity operator, we come up with this symmetry, right? Here we are coming up with this symmetry. Okay. So why to now just limit ourselves to r square? Now that we understand mathematically, this is giving me something beautiful. So let's just do something like this. So think about an abstract space, okay, complex space, having z1 and z2 as the vector, which you can write down if you want to, x1 I y1 and x2 plus I y2. So there exists something like R in C2 space and giving you something like this. I mean, where everything can be written like this. Now, do exactly what we did earlier. Exactly. So what will be our dagger? Now instead of RT, I will talk about our dagger. What will be that?
X
So
minus
x
iota
minus
y.
iota y.
Yeah,
X2
so
minus iota.
first let me just write down Z1 star, Z2 star, right? And then X1 minus IY1, X2 minus IY2, right? Yes, no.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, do R dagger times R. Give me the result of that.
Mod z1 square plus mod z2 square.
Mod Z1 square plus mod Z2 square, which is nothing but, if you think about it in this way, mod R square. Now in complex C2 space, okay, you have this length squared can be thought of what? I mean, this is what we did, mod Z1 square plus mod Z2 square. Let's think about, again going in the same line, let's think about a transformation U such that R prime results from this operation. It's a linear operator, so it will leave a vector in the same space. Yeah. So this, what kind of U is this guy now? So if you are representing your R by a matrix like this, what kind of matrix U will be?
Unitary.
At this point, it will be unitary. I mean, I did write U, but is it unitary? No, it's a 2 by 2 matrix, right?
2 cross 2, yes.
Yeah, it is a
Yeah,
2.
sir.
But
Yes.
what will be the element? It can be, let's say, any alpha, beta, gamma, delta. And remember that these can be complex entries, right? A general complex one, because your R prime is complex, R is complex. So this you can think about writing alpha 1 plus I alpha 2, beta 1 plus I beta 2, and same for this. So how many elements you are talking about here now? Last time you were talking about n square elements. Now how many elements are there?
2n square.
2 in square.
Right. Right. You have 2n square real, 2n square real coefficients there for these matrices. I mean, if you just want to write a 2 by 2 unitary matrix, you know real and the imaginary part. So there will be 2n square. Last time it was n square. Now, what did we impose? Impose the same thing here. R prime square. Let's say in
Potentially.
complex space, it leaves this, which is basically saying R prime dagger times R prime is equal to R dagger times R. Now, what will be the result of this guy?
Sir, U is unitary.
Right. So, how will you get this? R prime dagger will become R dagger, U dagger, and then UR is equal to R dagger R. Results in U dagger U is identity resulting in unitary matrices, or in this case we will get the matrices which are represented by unitary ones. In the real spaces they were the orthogonal one. All I have done is just extending the idea from the real space to the complex space, nothing beyond that. Right. Now, what are the properties of the unitary matrices?
Determinant is 1.
Okay, so I did write it earlier, but remember, do not forget about this mod here, because it means that U is written as, or determinant of U is written as, where theta is another real parameter. Not angle, but some parameter. Mod of determinant U is equal to 1. Rest everything is just like that. I mean, you have the two, so what did we wrote there? We wrote alpha, beta, gamma, delta. You can find out the constraints on that. In fact, let me just ask you to do that. So do this. U dagger is equal to I, fine, and U is given by a general matrix. So in the last case, we did it later on. But in this case, let's just start finding out the most general unitary matrix. So you will have U written like this. What will be U dagger? What will
Alpha
be
star, gamma star, beta star,
Alpha
delta
star,
star.
beta
alpha star, gamma star, beta star, delta star? And impose this condition U dagger equal to I. So give me something.
mod alpha square plus mod beta square
Okay.
alpha gamma star plus beta delta star
Plus beta delta star. Okay.
gamma alpha star
Okay. Alpha star gamma plus beta star delta. Basic complex conjugate of this one. And then this guy.
gamma square plus delta square.
And this will be equated to what? 1 0 0 1. So not all alpha, beta, gamma and delta are independent. Again, you will find out something similar what you were getting in the earlier case. Yeah, so you will find out that there exist constraints, but in this case look into this alpha gamma star plus beta delta star, and this is a complex conjugate of this. So the cross diagonal terms are complex conjugate, and remember this is something which I did earlier, that the complex conjugate z and z star, they are the independent parameters. Yeah, I mean when we discuss about the linear independence, we did this z and z star are independent. So in this guy, in this case, we have 4 of the constraints which are coming up because of this relation which you are getting. Now the 4 constraints means what? Our original U2, they were having 8 terms, and now you have 4 constraints. And then you will say, sir, but there is another constraint, that determinant U is equal to 1. And when we are writing this and we wrote determinant U is equal to I theta, suddenly what we find, that even though it's a constraint, but it will require me to also introduce one more parameter. So number of independent parameters in this case for the 2-dimensional complex space turns out to be 8 minus 4 minus 1 plus 1. And why I am writing minus 1? Minus 1 is a constraint which seems to come from determinant U is equal to plus 1, or mod of determinant U equal to 1. But then I need one more parameter to just explain this portion. So I just added one more parameter, and you will get exactly what? 4. So what we will get that in order to get this U2 group, in order to get U2 group, you will require 4 independent parameters to generate it. So now I am following the technique which is coming exactly from my previous discussion. I started by saying that instead of having now a real space two-dimensional vector, it's a complex space two-dimensional vector. I require now invariance under this rotation in this complex space. The result will be that the any operator we are talking about turns out to be unitary operator, and we will figure out, since it's not a real dimensional space, it's a complex dimensional space, so I cannot give you any physical representation, although I can still tell you that there can be rotation in complex space, there can be reflection in complex space, which will be taken care of under this kind of matrices, which is what we are calling of U matrices or U2 matrices. And in order to figure out the number of independent parameters, we will have to again get the relation. And remember, the relation will again come from these constraints. And a very generic question which is asked, if a particular matrix, I mean alpha, beta, gamma, delta, if out of that only 4 are independent, can you write down in terms of only 4 parameters, the unitary matrix, so that it actually signifies it. So summarizing what I have said is that U2 group is a continuous group of 2 cross 2 unitary matrices under matrix multiplication. Order of the U2 group turns out to be 4, and in fact if you do the most general one, you will find out that you started with 2n square element. Out of that, n square elements are giving you constraint. So you will find out that this kind of structure will come, and how many independent elements that means we are going to have. So 2n square to begin with, 8 elements, and 4 were the constraints. So this will turn out to be n square. And this guy is the order of our in general UN parameter, but here this for n is equal to 2, this turns out to be equal. Now again I will just follow the line, I will form SU2 group. Now what will be SU2 group? It will be exactly same, continuous group of 2 by 2 unitary matrices under matrix multiplication. Of course determinant U is equal to 1, or determinant U is equal to EI theta. And what will be the difference with SU2? What is special about this guy? What is this special?
Determinant equal to.
Now look into it. Determinant of U plus 1. Compare it with what we had in orthogonal groups. In orthogonal group, determinant of U was taking its value plus minus 1, and we were choosing only one value, which was determinant U is equal to plus 1 when we were going for the special group. In the unitary group, when we are saying mod of determinant U is equal to 1, there are infinitely many possible values, e raised to power I theta, where this theta, of course, you understand, this theta can be any real parameter and can be any continuous parameter. I am going to choose only one value, determinant U plus 1 out of all possibilities. So this, in the case of unitary matrices, this special condition is actually restricting from infinite many possibilities to a single possibility. Whereas in the case of SO2, it was just restricting out of 2 possibilities, I was restricting to 1 possibility. So in this case, since my determinant U is equal to plus 1 is basically equivalent to saying that I can drop this parameter theta. So what will be the order of this SU2?
3.
This will be 4 minus 1 equal to 2, 3, or in general for any order which we will write down SUN, it is equivalent to saying n square minus 1. So we are extending our knowledge of ON group and SON group to now complex spaces and come up with the idea of U2 and SU2, and of course we will further do this to do UN and SUN group. So I can just quickly write down that and then I will invite questions. So I can write extending the idea. What will be UN? It is N cross N unitary matrices. Of course, all the condition of the unitary is there. Yeah, and then you have a subgroup which is same as N cross N unitary matrices with this special condition that determinant of these U's will be restricted to 1. I keep on writing one thing time and again just to more emphasis on it, nothing beyond it. Okay, order of our UN group will turn out to be N square, whereas order of our SUN turns out to be N square minus 1. I will invite questions here. Yes.
So can we calculate the order of group by the that method that you told?
Of course, I mean actually order of the group is calculated using that. But remember that you have already done your orthogonal matrices, you have already done your unitary matrices. If I talk about the orthogonal matrices, how did you start with? Remember, you start with saying a general matrix 2 by 2, 4 elements, right? If I say it's a, let's say a symmetric matrix, how many independent components are there? Symmetric matrix. Out of 4, are all 4 independent symmetric matrices? What are symmetric matrices, by the way?
Sir, 3 are independent.
Transpose equals to the matrix.
A transpose is equal to A.
Right. So that means 3 are independent. That's a symmetric. What about the skew symmetric or anti-symmetric?
Sir, 1.
1. And how do you get it? Diagonal components are also now 0, skew symmetric, right? And the off
Yes.
diagonal component, one can be free, another will be minus of that, right? So similarly, in the same vein, you can continue to do something about the orthogonal matrices. It's not about the group, it is about knowing how the orders are found in the orthogonal matrices. Remember, the group is saying that the number of independent components out of n cross n will be just n square in the UN case, and earlier which we what we did, n minus n into n plus 1 over 2 for n square minus n into n plus 1 over 2 for our orthogonal matrices. It is coming from the knowledge of the orthogonal matrices. You can actually find out all the orders from there itself, and that's why I do not want to emphasize much on that, except in the unitary case there is a change in the order of the subgroup when you go from UN to SUN, which you will find that there is no change in the order of the subgroup when you go from ON to SON. That's the interesting aspect. Nothing beyond that is interesting. I mean, it's coming from that. In fact, I have already given you a question. Please do that. I mean, I generally ask all of us to do that. For O2 matrices, I have given you A, B, C, D. Find out the most general form. And for U2 matrix, which is I have given alpha, beta, gamma, delta, find out the most general form. This should have 4 components, because those are the 4 independent components in terms of which you are going to write. And here you will have 1 component. In fact, you will see that you will first write 2 components, and then you will say, okay, 2 components will again be related by some other constraint, which is determinant of O. So please do that. In fact, this is very important question. So yes, it can be done just by looking at the matrices. No need to think about it from anywhere else. Now, one question I'm pretty sure which comes to your mind, सर ये कॉम्प्लेक्स स्पेस में आइडिया को एक्सटेंड करके मिलेगा क्या? आई मीन रियल स्पेस में तो वी आर लिविंग अवर लाइफ. यू सेड SO3, आई मीन आई सेड SO3 is angular momentum. Fine, I mean it is angular momentum. Now, what are we gaining by doing this? Is any physics coming out of it? That's the question which you can ask. Does anybody know any physics which comes out of think about rotation in complex space? Okay, order. What will be the order of that SU2? Yeah, what will be the order of SU2? Can somebody remind me?
3.
3.
Three, sir.
Okay, good. Okay. Now, rotation in complex space.
Sir, one thing like the spin matrices that we have, they are also kind of unitary matrices.
That they are not, I mean, in principle, they are Hermitian because spin is an observable, but that matrix structure is definitely, yeah, I mean, interesting. You are saying that. So I will come to that surely, but it is this portion which relates rotation to spin. When you read about the spin angular momentum, you somehow started saying that it is rotation of some kind. Yeah, I mean, you started first, we initially started saying, okay, let's consider it that the particle, the fundamental particle can actually, or any particle can actually rotate, first the revolve, which will generate the angular momentum. So revolution around the origin. And then we can say, okay, it can also rotate around its own axis. Yeah. So there is a revolution as well as rotation, and this rotation generates what? So revolution generates angular momentum, which is called the orbital angular momentum. And this rotation generates what?
Spin.
We call that as the spin angular momentum. In fact, the word spin is coming from that, right? I mean, to begin with, we started saying that. But then later on, we found out, okay, it cannot be a real spin anyway. Why it cannot be a spin in a real dimension? Have you heard of any consequence of that? If electron is spinning to generate the angular momentum, what is electron does, then what will be the rotational velocity which will come out to be? It will exceed
Speed of light.
speed of light. So that cannot be a physical rotation. But also other things. Think about a fundamental particle which does not have a structure. And we are saying that it is rotating around an axis which is passing through it. But if the particle does not have any structure, from where this rotation we will start with, because there is no dot in it, there is no center in it. So that doesn't mean anything. So what does it mean to say when we are saying that it is a rotation of some kind? That what we say is that now making the concept abstract. What is the abstract nature of the concept? If we just think about the rotation in two-dimensional complex space, then the corresponding elements we are going to talk about would be the spin angular momentum, just like the way we said the three-dimensional SO3 is related with physical angular momentum. We will say two-dimensional SU2 will be related with spin angular momentum. The word rotation is still sticking, but it is no longer the rotation in a physical space or the real space. It's the rotation which is now taking place in some abstract space, which we call as the complex space. Remember, complex space cannot be visualized. So SU groups will become very important when we are going to explain a spin angular momentum, for example. SO groups will become very important when we are going to explain orbital angular momentum. And remember, then there is not only the L and the S aspect, you will have to figure out a way of adding the angular momentum, L and S first, and if there are two particles, then you have to have a way of adding J1 and J2. All of this is coming out of the natural consequence of the group theory. So a group theory is now giving you an idea what the spin angular momentum is. So if somebody asks a group theorist, what is an angular momentum? Oh, it is nothing but the invariance of space, invariance of length squared in complex 2 cross 2 space or complex two-dimensional space. Nothing beyond that. So mathematician, it is very easy to say. Physics, I have difficult times thinking about what is happening, in which space this rotation is happening. But the problem comes here. The, whatever you do with this will be able to explain the results which you are going to get, and hence you have no other way but to involve your unitary spaces, what we call as the complex spaces in your quantum mechanics. And that is why it is called, or it is said, that whosoever says that that person is not offended or confused by the nature of the quantum mechanics, that person has not understood it. Remember, it's the famous Niels Bohr statement. It's mind boggling, not mind blowing only. It's just not clear where is this rotation happening. But if you say that there exists SU2 group, it will explain everything related with spins. And the polyspin matrices will come as a natural consequence, which I will show to you in my remaining two classes. At this point, I just want to, I'm taking a pause, not a stopping here, but just to tell you that the idea of the group theory relating it with the symmetry is that the length square is invariant under a particular transformation, that is giving variety of things in physics. And that's why you will find out books on group theory in quantum physics, group theory in particle physics, group theory in nuclear physics, because these are the places which are basically uh, the direct implementation of the quantum mechanics. So field theory, particle physics, nuclear physics, you cannot even think about moving further without the basic knowledge of the group theory. Okay, questions, invite.
सर प्रीवियस पेज दिखाना है
जी.
All right, sir. Thank you.
Okay. Yeah, I mean, you can frame your questions. This is again, it's interesting. Whatever I am doing is coming out of Afghan book. It may be just that Afghan is not explaining all the concepts in the manner in which I am trying to explain to you. That the groups, if you just go back to my original place of the continuous groups. Now, these continuous groups play a very important role in physics. ON, SON, UN, and SUN are particularly important because it will be corresponding to our angular momentum algebra. I mean, this is what we get after that, out of it. SO3 is orbital angular momentum. SU2 is spin angular momentum for a group theorist. It's coming out naturally. Why continuous groups? Because they are all now getting generated. All the elements are generated by the variation of one parameter in O2, for example, and three parameters in SO3 in O3 or SO3, for example. Okay, I cannot stop here. I will just do something which I said I will be doing. What? An interesting consequence of the group theory. Okay. Can I talk about a group O1? How many independent parameters it will have?
One.
One.
So how are you getting it? N square minus n into n plus 1 over 2. So if n is equal to 1.
0.
0. And if there is 0 parameter, that means what? The group cannot be even generated, right? So O1 group does not even exist. O1 group does not even exist. So, and so is SO1. It cannot even exist. This cannot exist. What about U1, by the way? Remember the parameters 2n square minus.
It will have.
Yeah, so 2n square
1
minus
element.
n square, which is
N
n
square.
square. And if I try to generate SU1, then what will happen to this? X square minus 1. So this guy will not
0.
add. So this guy will not. But this will exist. What kind of group U1 would be? That is interesting to think about. What kind of group I am talking about? So this kind of group is something which takes Z to Z prime and relate it like this. So I can talk about a group U1 or U1, which is nothing but a collection of EI theta, where theta being real, of course, and 0. What is this guy doing, by the way? Can anybody tell me? Z prime equal to ei theta z.
It's a phase shift.
Right. Remember, this is what we say. Then what can you say about xi prime and xi representing? Both of them will be representing the same probability. Mod xi prime square will be same as mod xi square, right? So this is what we call in physics phase transformation. It is only the phase which is transformed and nothing else. So you can have infinite possibilities for this theta, and I am saying that okay, let's just take theta 0 to 2 pi. Now think about something, composition. So u theta 1, u theta 2, that I am going to apply first phase and then I am applying second phase, and what will be the result? E of I theta 1, E of I theta 2. So under simple complex multiplication, what will be the result? This will be E of I theta 1 plus theta 2.
Theta.
And this EI of theta 1 plus theta 2 is exactly of the same nature, E of I theta. So this guy confirms that there exists closure in this group. Can you think about other properties? Identity. What will be identity? U of 0, right?
Yeah.
Or U of 2 pi. I mean, in case if you want to think about it that way, but there is an identity element u0, and since I generally avoid writing 2 pi with equal to sign, so I just take 0. What about the inverse? Is there an inverse in this that will take the phase back?
Minus theta, u of minus
U of
theta.
minus theta or u of 2 pi minus theta, right? And you will see that again associative property will hold true. So, okay, I mean, I could have asked this question in a very simple way, just like the way I have asked. Will the group of phase transformation, will a set of phase transformation under the composition u theta 1 times u theta 2, which is the composition law that first you will apply one and then other, is it going to be a group? And you will basically show all these 4 properties that yes, u1 is going to form a group. Okay, now what am I interested in doing, which is okay, let's the last thing for today's class. R theta was a group. What was this group? Can somebody now remind me?
Cos theta minus sin theta.
Cos theta, okay, the way I wrote is cos theta, sin theta, minus sin theta and cos theta. This is what I wrote. Yeah?
Yes, sir.
Okay. Now, is this looking block diagonal or diagonal in any way?
No, sir.
No, it is not looking as diagonal or block diagonal in any way. Now, can you find out the eigenvalues and eigenvectors? So, what am I doing? Basically, I'm interested in doing
Diagonalization.
diagonalization, right? So diagonalization. Can somebody quickly tell me what are the eigenvalues? Eigenvalues. You will get complex eigenvalues, by the way. Interesting.
Cos theta plus iota sin theta.
So lambda 1, 2. You should be getting 2 of those eigenvalues because it's a 2 by 2 matrix. Cos theta
Yes. Plus
plus
iota
I,
sin theta.
but there should be one more.
Plus minus iota sin theta.
Right. So this can I write it at E plus I theta and E minus I theta?
Yes, sir.
Yeah. Okay. Others. Can somebody else comment on this? By the way, we gave this as one of the questions in internal assessment exam long back. Just find out the eigenvalues and the eigenvectors. Okay. So can somebody just say that E I theta and E minus I theta, they got this one? Just
Yes,
this.
sir.
Okay, you got that. So please find, okay, let me just give that eigenvectors of this. But one thing is for sure. Now that you have found the eigenvalue and I diagonalize R theta, do you know what will come as the diagonalized matrix? After doing
Iota
this,
e raised to power iota theta and e raised to power minus iota theta sitting on the diagonal terms.
excellent, excellent. Because I mean, whatever the diagonalization will do, ultimately your eigenvalues will form these portions. Yeah, I mean, this is what is supposed to be. But please do that. I mean, as a homework, please find out the eigenvectors, figure out that you are actually getting this r prime theta as your like diagonalized matrix. What have you got here in terms of our discussion of the previous classes and the summary of the earlier classes? What we have got, this guy r theta and r prime theta in terms of representation, what do we call these kind of representations? Both are related by transformation.
Similarity.
No, those representations which are related by similarity transformations are called equivalent trans representations. So these two are equivalent representation. But now look at the structure you have got. It's a diagonal one, which means what? As soon as you get the diagonal structure, both unit elements, so you can write down, this is the group which I just gave to you, ei theta, and another direct sum which is u minus 1, which is nothing but the minus of that. So what you have said is pretty interesting, that rotation matrices, which is 2 by 2 representation, can be reduced to irreducible representations u1 and u minus 1. But there is only one catch. I mean, it's not a catch, but it's the, I mean, I would say the consequence, that the real representation are now written in terms of complex representation. Remember, u1 is a complex ei theta 1 cos theta plus I sin theta, and u minus 1 is ei theta in minus I theta. So you have got the irreps u1, which is coming out of O2 or SO2, which was your rotation matrix. So SO2 representations can be reduced to irreducible representations u1 and u minus 1 using the group theory approach or the representation theory approach. This is what we called as the direct sums of u1. And please see the example 17.2.3, which is exactly what we have done here. The difference with respect to 17.2.2, here we are talking about continuous groups, and we have reduced our SO2 group, which is the rotation group, in terms of two U1 groups, U1 and U minus 1. So now I am basically relating the concepts which you have studied earlier in terms of what we are doing at present. The rotation matrices, which is SO2, can be thought of the direct sum of unitary matrices U1. And remember, I showed both of them are nothing but the groups. So I showed U1 as a group here, and earlier in my class I showed R theta forms a group under compositions. Questions here? This is example 17.2.3 of Afghan. Too many things happening
So,
together. Yes.
so in the example 17.2.2 in the Afghan, we
Yes.
have chosen V that has transformed all the matrices in the
Yes.
block diagonal. So
Yes.
how we can choose V?
Yeah, I mean, in the questions, see 3 by 3 matrices, when you are going to do it, of course, you will have to find out the eigenvalues and the eigenvectors the way we found out, right? The
Yes,
way
sir.
it is, right? So, but in that case, it's not that simple, because you will see that each of these eigenvalues which you will get to begin with, they may be degenerate ones. And whenever the degenerate eigenvalues come, there are a lot of possible eigenvectors which can be formed. Yeah. But it
Yes,
is
sir.
more or less coming out of that only, that you are constructing your, just remember that for at least for the examination purposes, diagonalization will be done by finding out the eigenvalues and normalized eigenvectors. Fine. So it is done exactly in that manner, to be honest. There also it is done in that manner. It is
Okay,
just
sir.
that there we have plenty of options of choosing, and you have chosen one, because remember, whenever there are degenerate eigenvalues, what happens in degenerate eigenvalues, that you can choose linear combination of any of the three general vectors, and those three linear vectors, once you normalize it, they will turn out to be something, I mean those some numbers. And here basically they did the same thing, they did not do anything else. So the concept is coming from the similarity transformation or the unitary transformation. Wherever you get in your question exam paper, every time you see that I'll have to diagonalize, just remember the concept which you have already used in your internal assessment question, part 4 of question 1. But you do that, I find that several one of you have diagonalized it, but they don't remember the basics. They don't remember that ultimately the diagonal matrix which has to come will have the eigenvalues which will go on the diagonal places, and off diagonal places will be 0. I mean, that is how the diagonalization works, right? This is the whole purpose of diagonalization. So please don't forget about that. Anything else? Kuch aur? Okay, so what I'm going to do in rest of the 2 classes, क्योंकि I'm left with only 2 classes, I'm just going to show you कि कैसे ये जो SO3 से angular momentum algebra है, we just make out of that. I will show you through the group theory approach of the continuous groups, which is contained in what is called the Lie groups, LIE. After, not, it is not a lie group. I mean, it doesn't lie. It is after famous physicist Sophus Lie, that we call these Lie group. LIE spelling is same as lie, but the groups won't lie. The groups will actually speak truth about several structures. We are just going to do those 2 things in our next 2 classes, and then we will basically formally wrap up the course. Okay, guys.
Thank you, sir.
Yeah, so I'm going to
Thank you,
upload
sir.
my
Thank you,
notes
sir.
immediately after the class, so that you can just go through the notes. You have questions, feel free to ask anytime. I mean, do not worry about it that the course is ending and hence teacher may or may not be approachable. Teacher will be approachable. Most likely after 21st onwards, I will be sitting even in my office. But don't worry about it. If those of you who are here, they can come to the office. Those of you who are not here, they can just basically ping me on my Teams account or Gmail or wherever. Teams is the simplest way to work, because there you can actually upload everything and we can discuss there. But otherwise also, I am approachable. Yep. So let me just do that. Thank you, guys.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank
Thank
you,
you,
sir.
sir.
Yep. 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 Yep.